Okay, let's do another example of finding this thing called heat of formation. Okay, let's try one. Let's try a question. We're going to say find the heat of formation delta HF of butane C4H10. So what we're looking for, delta HF equals blah. Okay. Here's what we know. We're trying to find the heat of formation of butane. In other words, the equation we're looking for is one where we are assembling butane from carbon and hydrogen. Well, how many carbons will you need? 4. How many hydrogens will you need? 10. But you guys know how this works. You can't have 10 H's, but you can have 5 H2s. And so this is what we're looking for. Okay? We know that we're going to need some other information here. In fact, we know from this table that the heat of combustion of butane here, negative 2,877.6 kilojoules. So if we know the heat of combustion, we can write the combustion equation to look like this. C4H10 is going to combine with oxygen. Our products are always carbon dioxide and water. And let's balance this because we're getting pretty good at this. We're going to need 4 carbons. We're going to need 10 hydrogens, and that means that we're going to need 13 oxygens, right? 8 and 5. So we'll look at it like this, and we'll say that the delta H of combustion we said was 2,877.6. Negative 2,877.6 kilojoules per mole. Okay? We're not really worried about the mole part. All right. So we want to get this equation, one of our step equations, to equal our target equation. So the first thing we want to do is flip this equation around to make C4H10 a product. So that means that we are going to have 4 CO2 and 5H2O yields 13 halves of an O2 and C4H10. When you do that, that makes this now a positive value. Okay, we've run it backwards. That's now positive. All right. So we got the C4H10 part of our target equation. Remember, this is the target equation. What we want to do is come up with a couple of step equations that produce the 4C and the 5H2, and that will also help us to eliminate the CO2 and the 5H2O from one of our step equations. Because remember, we want our step equations to be the equivalent of this target equation, and that means that everything that appears as a reactant has to be a reactant. Everything that appears as a product has to appear as a product. Everything else has to cancel each other out. Okay? So let's try this. We want a step equation that will put CO2 on the product side, so it'll cancel out the one that's here on the reactant side. And if we were going to assemble 4 CO2, we want 4 C's and 8 O's, but you can't have 8, you can have 4 O2. Okay, now we know from this table that when you are making carbon dioxide, it gives off negative 393.5. Well, we're not assembling 1, we're assembling 4. So that means that if our delta HF for 1 was negative 393.5, we are going to make 4, so we'll multiply that by 4. So bust out your calculator, negative 393.5 times 4, and this is 1,574 kilojoules, and it's a negative number, 1,574 kilojoules. Okay? Let's do the same thing. Let me write that a little bit better. That looks awful. 1,574. Okay, let's do the same thing with our water. We want an equation that's going to put 5H2 on the reactant side, and also eliminate our 5H2O from the reactant side of one of our step equations. So we want 5H2, and let's specify that this is a liquid so that we will know what to look for when we get to our table. So that means that if we're going to make 5H2Os, we're going to need 5 H2s and 5 Os, but you can't have 5 Os. You can, however, have 5 halves of O2. And according to this table, making liquid water gives off 285.8 kilojoules. Well, we're going to multiply that by 5. So if it was negative 285.841, now we're going to multiply that by 5. And this is now negative 1,429 kilojoules. Okay, if we did this right, that should mean that everything that appears as a reactant in our target equation should appear as a reactant in our step equations. Everything that appeared as a product in our target equation should appear as a product in one of our step equations, and everything else should cancel out. So 4CO2 cancels out 4CO2. 5H2O cancels out 5H2O, and here we have 8 halves of an O2 with 5 halves of an O2. That's 13 halves, and that cancels out this. Now let's remember that this is just a bookkeeping method. It's just our way of determining a reaction's energy change from some equivalent reactions. Remember that Hess's law says that the overall change of a reaction is equal to all the steps, even if those steps are theoretical. So this is just for bookkeeping. We're not saying that this is how this reaction is going to work. It's just a method for getting the numbers, okay? And so let's do it. What we know is that these 3-step equations are our equivalent of our target equation. And that means that our energy change should be the equivalent of adding all these together. So let's have 2,877.6. We're going to subtract from that 1,574. And we're going to subtract from that 1,429. And we get negative 125.4 kilojoules. This is the heat of formation of butane. Okay, that's our answer. That's all we're looking for. Okay, so take it for a spin, and hopefully that helps.